Student, today we will start from the exercise question number 3.6. In this, in the button cell widely used in watches and the other device, the following reaction take place. So the reaction is given Zn plus Ag2O plus H2O. It gives Zn plus 2 plus 2Ag plus 2H minus. Determine delta G0 and E0 for the reaction. Here the reaction is given which is occur in the button cell, and for this reaction we have to find out the Gibbs energy and standard electrode potential, right? Now write the equation. Now any cell reaction can be divided into two half reaction, right? One is oxidation half and second one is reduction half. In this reaction zinc is oxidized because here oxidation number of zinc is 0 and here plus 2 means here zinc is oxidized from 0 to plus 2. So it is oxidation reaction, and oxidation always take place at the anode. So anode reaction will be Zn. It gives Zn plus 2 electron, right? At the anode the zinc will donate 2 electron. Now other reaction will be carried out at the cathode. So cathode will be Ag2O plus H2O plus 2 electron, right? The 2 electron are accepted by the cathode, and this Ag2O converted into Ag plus 2OH minus, right? For the E0 cell we want E0 cathode minus E0 anode, right? Here at anode Zn plus 2 to Zn reduction potential is minus 0.76, so E0 anode is minus 0.76. At cathode there is a two molecule Ag2O and H2O, so we have to add them potential. The potential of Ag plus 2 Ag is 0.80 volt and E0 OH minus 2 H2O is minus 0.456 volt, right? Add them, you will get the E0 cathode equal to 0.344 volt. Now replace that value, you will get the E0 cell. For this reaction it will be a 1.104 volt. Now you also have to find out the Gibbs free energy. Gibbs free energy delta G0 is equal to minus NF E0 cell, right? During reaction the electron donating or accepting are 2 electron, so our N will be 2. The Faraday value is 96500 and you get E0 cell 1.104. so multiply them and you will get the Gibbs free energy minus 213.07 kilojoule. Now question number 3.7. Define conductivity and molar conductivity for the solution of an electrolyte. Discuss their variation with concentration. Here we have to find out the conductivity and molar conductivity, and also we have to discuss the change in conductivity and molar conductivity with the change in concentration, right? You already studied that topic, this topic in the theory. Now see how to write. Conductivity. Conductivity of a solution is defined as the conductance of a solution per unit volume. Means conductivity is nothing but the number of ion present in a per unit volume in a given solution, right? If any solution is given and if we take the unit cell, unit volume, right? In this volume the number of ion present is known as the conductivity, right? It's also reciprocal of resistivity. So you can write the conductivity is equal to 1 by resistivity. The resistivity is denoted by rho. Now unit of resistivity is ohm into centimeter. So unit of conductivity will be a ohm inverse into centimeter inverse. Ohm inverse is known as mho, so you can write that mho centimeter inverse, or also you can write the Siemens centimeter inverse. Now you have to discuss the variation of conductivity with the concentration. Now if we take the 500 ml solution and in that solution we add 5 gram of NaCl, right? The number of ion present in per unit, right, is greater than if we add that 5 gram of NaCl in the 1000 ml water, right? If we take that to solution, right? If we dilute that solution and make it to 1000 ml, the number of ion, we can see that the number of ion which are present in a per unit volume will be a decrease. So we can say that the concentration decrease, there will be a decrease in the conductivity, right? And for the weak and strong electrolyte both, this is applicable because the number of ion which are carried the current in solution decrease with the decrease in concentration. Now second one is molar conductivity. Molar conductivity of a solution at a given concentration is the conductance of a volume V of a solution containing 1 mole of the electrolyte kept in a between electrolyte, right? Here molar conductivity means if we take a solution, right, and add 1 mole of electrolyte, then the conductivity of that whole solution is known as a molar conductivity. Means the molar conductivity equal to conductivity into volume. Now if we take the concentration as a molarity, the molarity is equal to mole by volume, right? Here we are finding the concentration for 1 mole solution, so take mole 1, so concentration will be 1 by V, so you can replace V is equal to 1 by C, right? So molar conductivity will be a conductivity by concentration. Now multiply by 1000 because here the volume is, we take volume in a ml, right? So the molar conductivity will be a conductivity by concentration into 1000, right? Now unit of molar conductivity, the unit of conductivity is Siemens into centimeter and unit of concentration is the mole per centimeter cube, right? So you will get a unit of molar conductivity Siemens centimeter square per mole inverse, right? Now we have to discuss the change in conductivity. The molar conductivity increase with the decrease in the concentration, right? How? See that if we take two container, right, one having 500 ml solution and one having 1000 ml solution, in which we add 1 mole of electrolyte. In 500 ml solution, electrolyte will be converted into ions is less than in the 1000 ml, because here we have to see the ions in whole solution, right? Because lambda is equal to K into V, right? So number of ions will be increased in whole solution, right? So we can say that the molar conductivity will be increased with the dilution. Here the graph for the molar conductivity, this is a graph for the strong electrolyte and this is graph for the weak electrolyte. Exercise question number 3.8. The conductivity of 0.20 molar solution of KCl at 298 Kelvin is 0.0248 Siemens centimeter inverse. Calculate its molar conductivity. We have to find out its molar conductivity, which having formula conductivity into 1000 divided by concentration, right? Here conductivity and concentration both are given, right? Replace that value and simplify that. You will get the answer. Molar conductivity is equal to 124 Siemens centimeter square mole inverse, right? Question number 3.9. The resistance of conductivity cell containing 0.001 molar KCl solution at 298 Kelvin is 1500 ohm. What is the cell constant if conductivity of a 0.001 molar KCl solution at 298 Kelvin is 0.146 into 10 to the power minus 3 Siemens centimeter inverse, right? Here we have to find out the cell constant. Cell constant means conductivity into ohm. You study this formula in the theory, right? Here conductivity and resistance both are given, Just replace the value, multiply them, you will get the answer. The unit of cell constant will be centimeter inverse, because unit of resistance is ohm and unit of conductivity is Siemens into centimeter inverse. Siemens means ohm inverse and centimeter inverse. That ohm inverse and ohm will be cancelled out, so you will get the unit centimeter inverse. Alright. Now question number 3.10. The conductivity of sodium chloride at 298 Kelvin has been determined at the different concentration, and our results are given below. Here the concentration and conductivity are given for the different at the different concentration. Conductivity are given for the sodium chloride at 298 Kelvin temperature, right? For from this table we have to calculate the molar conductivity for this all values, and we have to plot a graph of lambda m versus root c, right? Lambda m versus root c, and we have to find out the lambda m naught, means the molar conductivity at the infinite solution, right? Now first of all, prepare a table, right? For plotting the graph we need the lambda m, so first of all prepare a table in which this is a concentration which are given in the question, right? Now take the root of these concentrations, right? Now conductivity is also given in the question. This is given in terms of 10 to the power 2 into conductivity, right? So 10 to the power 2 into conductivity. If we take a first value 1.237, then we can write like that, 10 to the power 2 into conductivity equal to 1.37 into Siemens meter inverse, the unit of this Siemens into meter inverse, right? If we take 10 to the power 2 other side, it will be converted into 10 to the power minus 2, right? Here the conductivity is given into meter inverse, we want it into centimeter inverse, so also multiply by 10 to the power minus 2, so you will get the 1.237 into 10 to the power minus 4, right? So write that conductivity in terms of 10 to the power minus 4, right? Now we have to find out molar conductivity, which having formula conductivity by concentration into 1000, right? For this all concentration and conductivity, find the molar conductivity. These are the answers of molar conductivity. Now we have to plot the graph for the conductivity versus root c, right? This is a graph of molar conductivity versus root c. For the graph, see the highest and lowest value of the lambda m and highest and lowest value of root c. According this value, take that values, right? And then one by one plot the points. First plot point at the 0.0316 and 123.7, alright? Suppose it is a 0.03 for this. This is a 1, 2, 3, right? And the intersecting point is our first value, right? Plot all points from this value, right? You will get a straight line. We have to extend that straight line. When it straight line intersect the y-axis, it will be our lambda m naught, right? So lambda m naught will be a 124 Siemens centimeter square mole inverse. Now question number 3.11. Conductivity of 0.00241 molar acetic acid is 7.896 into 10 to the power minus 5 Siemens centimeter inverse. Calculate its molar conductivity, and if lambda m naught for acetic acid is 390.5 Siemens centimeter square mole inverse, what is its dissociation constant, right? We have to find out the molar conductivity, means we have to find out the lambda m, and dissociation constant means alpha, right? Here these values are given for the acetic acid. The formula of acetic acid is CH3COOH. So acetic acid is ionized in that ion of CH3COO minus and H plus ion, right? For the initial, the concentration of acetic acid will be a C. The concentration of that ion will be a 0, right? At equilibrium of C alpha, concentration of ion will be produced. So concentration of acetic acid will be a C 1 minus alpha, right? Because here the concentration is C and the ions produce the C alpha, so subtract this concentration, you will get C1 minus alpha, right? Now first of all we have to find out molar conductivity. Its formula is conductivity into 1000 by C. In this equation the conductivity is given. It is our conductivity. If you didn't understand, C its unit. From unit you can easily conclude that which is conductivity, which is the molar conductivity, right? This is a unit of conductivity, so you can say that this is a conductivity, right? And this is a concentration. Replace those values and you will get the lambda m, right? Molar conductivity. Now you also have to find out the lambda m by lambda m naught, right? Lambda m you calculate and lambda m naught is given in the question. Replace those values, you will get the alpha. Now you have to find out the dissociation constant. Dissociation constant for the acid will be a Ka. Now from this equation you can say that Ka is equal to concentration of product divided by concentration of reactant. Cc will be a cancel out, so you will get the C alpha square by 1 minus alpha, right? Now replace the value of alpha and concentration, you will get the answer of dissociation constant. Dissociation constant will be a 1.86 into 10 to the power minus 5 mole per liter, right? Now question number 3.12, how much charge is required for the following reduction? Right here some reduction reactions are given, and for this reaction we have to find out required charge. The first one is the 1 mole of Al plus 3 to Al, right? We have to reduce 1 mole of Al plus 3 to Al. For the reduction of Al plus 3 there is a required of 3 electron, so we can say that 1 mole of Al plus 3 is required 3 mole electron, means required charge is 3 Faraday, right? Because 1 mole of electron is equal to 1 Faraday, means 3 mole of electron equal to 3 Faraday. Replace the value of Faraday and multiply by 3, you will get the answer. Second one, 1 mole of Cu plus 2 to Cu, means we have to reduce the Cu plus 2. For the reduction of Cu plus 2, there is the required electron is 2, right? From this reaction we can say that 1 mole of Cu plus 2 is required 2 electron to convert it in Cu. So required charge will be a 2 Faraday. Replace the value of Faraday and multiply by 2, you will get the answer. Now we have to reduce 1 mole of MnO4 to Mn plus 2. Means here a reduction of Mn plus 2 is take place. So first of all we have to find how many oxidation numbers are decreasing during the reduction. So first of all find the oxidation number of Mn in MnO4 minus. Here suppose oxidation number of Mn is X and 4 oxygen are there, so plus 4 oxygen, total charge is minus 1, so minus 1. Now the oxidation number of oxygen is minus 2, replace that, you will get the oxidation number of manganese is plus 7, right? If in MnO4 minus oxidation number of manganese is plus 7, it is converting into plus 2, means manganese accept or gain 5 electron, right? So we can say that 1 mole of manganese required 5 mole of electron, means required charge is equal to 5 Faraday. Replace the value of Faraday and multiply by 5, you will get the answer. right? Number 3.13. How much electricity in terms of Faraday is required to produce 20 gram of calcium from molten CaCl2 and 40 gram of aluminum from molten Al2O3, right? Here we have to find out the required electricity. First question, 20 gram of Ca from molten CaCl2, right? We have to deposit 20 gram of Ca from CaCl2. In CaCl2, the oxidation number of Ca is +2, so we can write that Ca +2 gain 2 electron, it converted into Ca, right? For this equation, we can say that 2 Faraday is required for the conversion of 40 gram of Ca. We have to deposit 20 gram. So we can write that electricity required to produce 40 gram of Ca is 2 Faraday. Then electricity required to produce 20 gram of Ca is how much? Cross multiply them. So you will get 2 Faraday into 20 by 40. So 1 Faraday means for the deposition of 20 gram of Ca from CaCl2, we required 1 Faraday electricity, right? Second question. 40 gram of Al from molten Al2O3, right? In Al2O3, the oxidation state of Al is +3. So we can write that Al plus 3 electron, it gives Al, right? So we required 3 Faraday electricity for the deposition of 27 gram aluminum, right? We in question 40 gram of aluminum is given, so we can write that electricity required to produce 27 gram of Al is 3 Faraday. Then electricity required to produce 40 gram of aluminum is how much? Cross multiply, you will get answer 4.44 Faraday. Means for the deposition of 40 gram of aluminum from Al2O3, we require 4.44 Faraday electricity, right? Now question number 3.14. How much electricity is required in coulomb for the oxidation of first 1 mole of H2O2O2 and second 1 mole of Fe2O3, right? Here two oxidation reaction are given, and for this oxidation we have to find out how much electricity is required in coulomb. Take first question. 1 mole of H2O to O2, right? We have to convert H2O into O2, right? According to the question, we can write that H2O, it gives H2 plus half O2, right? In H2O, the oxidation number of oxygen is -2, means we can write that only -2, it gives half O2 and lose 2 electron, right? Because this is oxidation reaction. For this reaction, we can say that electricity required for the oxidation of 1 mole of H2O2 is 2 Faraday, because there is a liberation of 2 electron, right? So replace the value of Faraday, you will get the answer in coulomb, right? Second one, according we have to oxidize FeO to Fe2O3, right? 1 mole of FeO to FeO3. In FeO, the oxidation state of Fe is +2, and in Fe2O3, oxidation state of Fe is +3. So we can write that Fe +2 converted into Fe +3 and donate 1 electron. So for this reaction, we can say that electricity required to oxidize 1 mole of FeO to Fe2O3 is 1 Faraday. Replace the value of Faraday, you will get the answer, right, in coulomb.